For 36 years, one single mystery sat quietly at the edge of our solar system, unsolved, untouched, resisting every instrument astronomers pointed at it. Every other giant planet in our solar system had already given up this secret. Jupiter had it, Saturn had it, Uranus had it. Only one world kept it hidden, wrapped in cold and darkness more than 3 billion miles from the sun. And then, in a quiet announcement backed by a brand new peer-reviewed paper, scientists confirmed they had finally caught it. A discovery so unexpected that the lead researcher himself admitted, on the record, that what appeared in the data left him genuinely stunned. This is the story of how the James Webb Space Telescope did something no instrument built by humanity had ever managed to do before, and what it found when it finally did. This is Neptune, the most distant planet in our solar system. A world so far from the sun that sunlight itself takes over 4 hours to reach it. So cold and dim that even our best telescopes have historically struggled to resolve any detail on its surface at all. And buried in its atmosphere was a phenomenon that scientists had been chasing since the summer of 1989, when NASA's Voyager 2 became the only spacecraft in history to ever fly past this ice giant up close, capturing a handful of brief, tantalizing hints of something glowing in Neptune's upper atmosphere. Auroras, the same shimmering, energetic glow that lights up Earth's polar skies, the same phenomenon astronomers had already directly imaged and confirmed on Jupiter, Saturn, and Uranus. But on Neptune, for 36 straight years, it stayed just out of reach. Suspected, predicted, modeled, never actually captured. Until now. To understand why this took so long, you first need to understand what an aurora actually is, and why it should have been easy to find on a planet this size. Auroras occur when energetic charged particles, most often streaming outward from the sun in the form of the solar wind, become trapped by a planet's magnetic field and funneled down into its upper atmosphere. When those particles slam into gas molecules at extremely high speed, the collision releases energy in the form of light, the same basic physical process responsible for the emerald and crimson curtains that appear over Earth's polar regions during a strong geomagnetic storm. Every giant planet in our solar system has a strong magnetic field. Every giant planet in our solar system is constantly bombarded by the solar wind, even planets sitting billions of miles from the sun. By every reasonable expectation, Neptune should have been producing auroras just as vividly as its planetary siblings. Astronomers had every theoretical reason to expect they would eventually find them. They simply could not see them. Part of the challenge was Neptune's sheer distance. It orbits more than 4.5 billion kilometers from the sun, over 30 times farther out than Earth, receiving a fraction of the sunlight, and astronomers assumed only a correspondingly faint trickle of the solar wind needed to power a bright auroral display. Ground-based telescopes, even the most powerful ones on Earth, simply lacked the sensitivity to pick out a faint auroral glow against the overwhelming background noise of observing a small, dim, distant world through the haze of Earth's own atmosphere. For over 3 decades, that specific gap in our solar system's family portrait remained stubbornly, frustratingly unfilled. Consider what that gap actually meant for the field of planetary science. Jupiter's auroras had been imaged and studied extensively, some of the most spectacular examples anywhere in the solar system. Glowing rings of ultraviolet light circling its poles, driven by a magnetic field so powerful it dwarfs every other planet's. Saturn's auroras had likewise been captured in detail, their subtle variations tracked across multiple missions and multiple decades. Even Uranus, a world nearly as strange and remote as Neptune itself, tilted onto its side so severely that its poles point almost directly at the sun during parts of its orbit, had already yielded a confirmed auroral detection. Every single other giant planet had, in effect, already told scientists its story. Neptune alone stayed silent, an obvious gap sitting right in the middle of an otherwise completed picture, nagging at researchers who understood on every theoretical level exactly what should be there, and simply lacked the tools sharp enough to actually see it. Voyager 2's brief 1989 flyby remains, to this day, the only time any spacecraft has ever visited Neptune directly. No orbiter has ever circled it. No lander has ever touched anything resembling its surface. Everything scientists have learned about this planet since that single encounter has come from telescopes staring across billions of kilometers of empty space, making every new data point disproportionately precious. That tool finally arrived in December of 2021, when the James Webb Space Telescope launched and began its slow, careful journey toward the second Lagrange point, a stable gravitational parking spot roughly 1 million miles from Earth, positioned to keep its sensitive instruments shielded from the heat and light of both the sun and our own planet. Unlike telescopes built primarily to observe visible light, Webb was designed from the ground up around infrared observation, tuned specifically to detect the kind of faint, long-wavelength glow that cold, distant objects like Neptune actually emit. It was, in a very real sense, purpose-built to eventually succeed at exactly the kind of detection that had eluded every previous instrument for more than 3 decades. Then, in June of 2023, scientists turned the James Webb Space Telescope toward Neptune, using its near-infrared spectrograph instrument, an instrument capable of reading the precise chemical fingerprint of light coming from an object by breaking it apart into its component wavelengths, revealing details invisible to conventional imaging alone. The observation was part of a guaranteed time program led by Heidi Hammel, a Webb interdisciplinary scientist with the Association of Universities for Research in Astronomy, specifically designed to study the solar system's outer planets in detail no previous instrument had been capable of achieving. And in the data that came back, the science team, led by Henrik Mellon, then working at the University of Leicester and now at Northumbria University, found exactly what generations of astronomers had been hunting for. An extremely prominent emission line in Neptune's spectrum, the unmistakable signature of a molecule called the trihydrogen cation, written by scientists as H3+, a charged particle known to form specifically as a direct byproduct of auroral activity in a planet's ionosphere. It had already been detected as a clear marker of auroras on Jupiter, Saturn, and Uranus. Finding it at Neptune, glowing in the data with striking clarity, was the confirmation astronomers had been chasing for 36 years. Mellon did not hide his reaction. Turns out, he explained, actually imaging the auroral activity on Neptune was only possible with Webb's near-infrared sensitivity. He described the moment plainly, saying it was stunning not just to finally see the auroras confirmed, but to see the sheer detail and clarity of the signature, a level of precision that genuinely shocked him as he analyzed the results. Heidi Hammel, reflecting on the decades of failed attempts that came before this observation, noted that H3+ had long been the clear, reliable signifier of auroral activity on every other gas giant in our solar system, and that scientists had expected year after year to eventually find the same signature at Neptune using the best ground-based facilities available to them. Only with an instrument like Webb, she said, did that confirmation finally arrive. The resulting image itself, released to the public alongside the peer-reviewed findings, showed Neptune rendered in soft, multi-hued blue, with faint cyan patches of auroral glow layered directly over the planet's familiar cloud features, a level of visual detail on this distant world that had simply never existed in any previous photograph. But the discovery did not stop at simply proving the auroras existed. What Webb's data revealed next turned out to be even stranger, and it forced scientists to reconsider something fundamental about how they had been picturing this planet for over 3 decades. On Earth, auroras cluster near the north and south poles, because that is where our planet's magnetic field lines converge and funnel charged particles down into the atmosphere. Astronomers expected something broadly similar at Neptune. Instead, the Webb data showed the auroral glow appearing not at Neptune's geographic poles, but at its mid-latitudes, roughly the equivalent, in Earth terms, of where South America sits on our own globe. A location nobody was specifically expecting the brightest auroral activity to appear. The explanation traces back to one of the strangest features of Neptune itself, a peculiarity first uncovered during that same brief 1989 Voyager 2 flyby. Unlike Earth, where the magnetic field lines up reasonably close to the planet's rotational axis, Neptune's magnetic field is tilted by a full 47 degrees relative to the axis the planet actually spins on. It is not just off-center, it is dramatically, almost chaotically skewed, offset from the planet's core in a way that remains only partially understood even now. Because auroral activity forms wherever a planet's magnetic field lines actually converge into the atmosphere, and because Neptune's magnetic field is tilted so far from its rotational poles, its auroras appear scattered across its mid-latitudes instead of clustering neatly at the top and bottom of the globe the way Earth's, Jupiter's, and Saturn's do. It is a visible, glowing consequence of one of the strangest magnetic fields anywhere in our solar system, now finally captured directly in detailed infrared light for the very first time. And there was one more result buried in that same dataset, arguably the most consequential piece of the entire discovery, because it did not just confirm something scientists were hoping to find. It answered a question nobody had even fully known how to ask. Using the same spectroscopic data, the research team was able to measure the actual temperature of the top of Neptune's atmosphere, its ionosphere, for the first time since Voyager 2's flyby in 1989. And what they found left Mellon, in his own words, astonished. Neptune's upper atmosphere had cooled dramatically by several hundreds of degrees over the past 3 decades. The temperature recorded by Webb in 2023 was just over half of what Voyager 2 had measured back in 1989. Sit with that for a moment. A planet sitting more than 4 billion kilometers from the sun, a world so distant and so cold already that its baseline temperature barely rises above -200 degrees Celsius, somehow grew dramatically colder still. its upper atmosphere shedding an enormous fraction of its heat over a span of just 34 years. And that dramatic cooling turned out to be the missing piece explaining the entire 36-year mystery. Astronomers had spent decades predicting how bright Neptune's auroras should be based directly on the temperature Voyager 2 had recorded in 1989. But a colder upper atmosphere produces a measurably fainter aurora. As Neptune's ionosphere gradually cooled over the following decades, its auroral glow dimmed right along with it, fading further and further below the detection threshold of every telescope, on or near Earth, hiding in plain sight, exactly where astronomers had been looking all along, simply too faint by the time anyone with sufficiently sensitive instruments finally looked. That single temperature measurement opened up an entirely new, unexpected question. Why did Neptune's atmosphere cool so significantly in just 3 decades? Nobody fully knows yet. It suggests that even a world sitting more than 30 times farther from the Sun than Earth, a planet many assumed would be essentially frozen in a fixed, unchanging state, is still capable of genuine, measurable, dramatic atmospheric change over a surprisingly short span of time. It raises questions about solar activity, about the 11-year solar cycle that governs how much energy and radiation the Sun sends outward through the solar system, and about processes inside Neptune's own atmosphere that remain largely unexplained. It is the kind of finding that answers one long-standing mystery while immediately opening several new ones in its place, which is precisely what a genuine scientific breakthrough tends to do. It is worth pausing on just how strange this cooling trend actually is when compared with what scientists observe on Earth. Our own planet's upper atmosphere responds to solar activity too, warming and cooling in step with the Sun's roughly 11-year cycle of magnetic activity. But those swings are generally modest, and Earth sits close enough to the Sun that the connection between solar output and atmospheric temperature is at least reasonably well mapped. Neptune sits so far from the Sun that many researchers assumed its upper atmosphere would be largely insulated from that kind of solar-driven variability, ticking along at a slow, steady, nearly unchanging temperature, regardless of what the Sun happened to be doing millions of miles away. Finding that its ionosphere had lost roughly half its heat in just over 3 decades directly challenges that assumption. And it means the connection between solar activity and atmospheric behavior on the outer ice giants may be far stronger and far less understood than anyone had previously modeled. It also means that whatever future missions eventually get built to study Uranus and Neptune up close, something NASA and other space agencies have discussed for years without yet committing to launch, will need to treat these worlds not as static, frozen curiosities, but as genuinely dynamic environments capable of significant change within a single human lifetime. Lee Fletcher of the University of Leicester, a co-author on the published research, framed the discovery as more than a single successful observation. As scientists look ahead toward potential future missions, specifically targeting Uranus and Neptune, he explained, this result makes clear just how essential infrared-tuned instruments will be to continuing this work. Webb, he said, has finally opened the window onto this last, previously hidden layer of the outer planet's upper atmospheres, the ionosphere, a region scientists had been unable to properly study on Neptune for the entire history of space exploration until this single set of observations changed that. The findings, formally published in the journal Nature Astronomy, mark the closing of a genuine decades-long gap in planetary science. For the first time, every giant planet in our solar system, Jupiter, Saturn, Uranus, and finally Neptune, has now been directly confirmed to produce auroras, each one captured, measured, and documented using the same reliable H3+ signature. Neptune was the very last piece of that particular puzzle, resisting confirmation for 36 years after Voyager 2's brief, fleeting glimpse first suggested something might be there. There is something worth appreciating in just how methodical this entire process was. This was not a lucky accident, a stray signal caught by chance during an unrelated observation. It was the direct result of a specifically designed research program, built years in advance by scientists who understood exactly what they were looking for, and exactly why previous instruments had failed to find it. Heidi Hammel had spent much of her career studying the outer planets, going back to the Voyager missions themselves, and the guaranteed observation time she was allocated as part of Webb's Cycle 1 science program was deliberately structured to finally close this specific, long-standing gap. That is worth sitting with, because it reflects something true about how the biggest breakthroughs in modern astronomy tend to actually happen. Not through sudden, unexpected accidents, but through patient, well-designed observation campaigns, aimed precisely at a question the scientific community had been unable to answer for a very long time, using an instrument built specifically capable of finally answering it. Scientists are already planning what comes next. Because Webb succeeded where every previous attempt failed, researchers now hope to observe Neptune repeatedly over a complete 11-year solar cycle, the recurring period during which the Sun's own magnetic activity rises and falls, driving changes in the solar wind that reaches every planet in the solar system, including one sitting nearly at the very edge of it. Tracking how Neptune's faint, oddly located auroras shift and change across that full cycle could finally offer real insight into one of the strangest unresolved mysteries about this planet, the true origin of its dramatically tilted, off-center magnetic field, and why it behaves so differently from every other magnetic field in our solar system. What makes this discovery worth pausing on is not just the image itself, striking as it is, with faint cyan splotches of auroral light glowing against Neptune's pale blue disk in a way no human eye had ever confirmed seeing before. It is what that image represents. 36 years of astronomers knowing something should be there, predicting it should be there, and quietly, patiently continuing to look, observation after observation, telescope after telescope, without success, until an instrument sensitive enough finally arrived in exactly the right position to catch it. Voyager 2 gave humanity a single, brief, imperfect hint in 1989, a fast flyby lasting mere hours as the spacecraft rushed past on its way out of the solar system forever. Webb, sitting in a stable orbit nearly 1 million miles from Earth, was able to look back at that same distant, dim world and finally deliver the answer 3.5 decades later, along with an entirely unexpected discovery about a cooling atmosphere that nobody had specifically gone looking for. That is the real story behind the headline, not simply a pretty new picture of a distant blue planet, though it is that too. A genuine scientific mystery, open since before most people watching this were even born, finally solved, and in the process of solving it, scientists discovered they had an entirely new mystery on their hands. A planet apparently cooling in ways nobody fully predicted, sitting quietly at the outer edge of everything we call home, still capable, after all this time, of surprising the people studying it. If discoveries like this keep pulling you back to look up at the night sky, subscribe, because Webb has years left in its mission, and Neptune, sitting quietly at the outer edge of everything we call home, still has more secrets left to give up.